agreed to answer questions about his talk a couple of weeks ago. For all of us who were there, even people who weren't there could have questions. A couple of weeks ago.
May I first ask the question of just terminology? You were telling it was n equals 4
right.
SU infinity.
Yes.
Now what does n equals 4 mean? It means 16 super...
It means 16 supersymmetries, yes. Yeah. And so it
I mean, is it possible to write down the model, or is it too long to do that?
do you want to just see the Lagrangian for the model, or well, no,
it Blackboard, I don't want to see it.
no, it's. I mean, the general structure is very easy to describe. Sorry?
Is it the one obtained by dimensional reduction from dimension A?
10.
So
Yes,
10.
it is exactly that one. Yes. So that's the easiest way of thinking about what it is. In 10 dimensions, there is the n equals 1 supersymmetric theory, which just has as its particle content the gauge field and the gaugino. So fermion, both in the adjoint representation of the gauge group. You take that theory in 10 dimensions, and you just dimensionally reduce to 4 dimensions, and that's the n equals 4 superagnos theory. Dimensionally reduced means that you that you just make all the fields only dependent, you know.
Oh, I see. So you just,
Yeah.
You just
So and
by
from
hand, you just require the fields not to have.
right, exactly. By hand, you just require them not to have any dependence on the other coordinates other than the first 4. And that immediately gives you an idea for just the particle content of the theory. So if I take the gauge field, if this isn't the index that runs from 1 to 10, then and let me let's say mu is the index that runs from 1 to 4, so it's our ordinary 4 dimensions. Then the bosons of the theory are the a mu and the am. So let's say m is 5 up to 10. These are 6 indices. Okay, so I have the a mu and the am, and so these are telling you that there's a 4-dimensional gauge field. So this is a spin 1 particle in 4 dimensions. These are 6 real scalar fields from the 4-dimensional point of view. They were part of a vector component in 10 dimensions, but there are 6 real fields from the 4-dimensional point of view. Okay. And similarly, if we take yes, they're all in the adjoint representation. So they all, all of these things have some index. So everything is in the adjoint representation of the gauge group.
Which you're going to be sending to infinity.
Yeah, we're going to be sending it to infinity. Yeah, that's right. It's a UN, and we send n to infinity. And not for this purpose. It doesn't make any difference. I mean, there is a difference, but there's a U1 part, but it doesn't make a difference here. And similarly, you have a fermion in 10 dimensions that when you reduce to 4 dimensions is 4 Weyl fermions in the adjoint representation again. So when we reduce all of them, we have one of them, well, we have 4 fermions in the adjoint representation again. So you see if you just count the total number of, so these are 4 complex fermions, okay? So if we count the total number of degrees of freedom, there's 2 degrees of freedom in the spin 1 gauge field. Well, it really looks like 4, but there's a gauge symmetry, so there's a gauge redundancy. There's only 2 degrees of freedom. They correspond to the 2 helicities of a massless spin 1 particle. So there's 2 here, plus 6 is 8, and there's 4 complex, so 8 real degrees of freedom for the fermion. Now, and we could write down the Lagrangian straightforwardly. So we have the usual trace F squared for Yang-Mills theory. Then there are similar kinetic terms for these scalars, which are conventionally denoted as, so there's 6 of these phi's, d phi I squared, the sum from I equals 1 to 6.
Bosons or not?
These are bosons, yeah, these are bosons.
Couple of direct, yeah.
Right, then we have these 4 fermions. Okay, and there are 4 of these, so you sum over alpha equals 1 to 4. And then there's various other interactions apart from just the gauge interactions. For example, we have interactions between a scalar and 2 fermions. Okay? And we also have interactions between scalars that look like things that look like that, phi I and phi j squared. Okay?
This
Yeah.
is in 4 dimensions?
This is in 4 dimensions. This is in 4 dimensions. Yeah, yeah. This is now part of the point of the sort of process that we're talking about is actually you never have to talk about the Lagrangian, which is good. Lagrangian is a little bit complicated, and there's a much simpler way of talking about the processes. So what we're interested, I mean, when you have a Lagrangian, you can do many things with it. What it's really built for is to ask very local questions. Like, well, it's clearly it's a local object. You integrate it over space-time. You can ask about things like correlation functions. You can ask local questions. The questions we're interested in are just by design are less local questions to begin with. We're sending in a bunch of particles from infinity. They bang into each other. They go back out to infinity. And the initial and the final states are really measured at infinity. So
Are you really looking at S matrix?
we're really looking at the S matrix. Yes, we're looking at the S matrix directly. Right.
Are these particles going to be massive or massless?
They're massless. They're massless for these. Yeah.
Conformal symmetry.
We have conformal symmetry. We have sorry.
It's not broken.
That's not broken. Now it's not broken classically, or what's the same as far as the scattering process goes. What's known as the tree approximation. It's not broken at tree level, right? It, in fact, typically is broken at higher orders. The reason it's broken at higher orders is that I mean, it might help if I started writing some specific formulas. But the reason it's broken at higher orders is that while these tree processes are well, they're nice rational functions of the external momenta. Okay, so you send in a bunch of particles. The tree amplitudes are nice rational functions of the external momenta. But that means they have poles. They have poles in certain places. And the poles all have sort of physical interpretations. The poles arise when you have, for example, you have a particle moving along, and there's the emission of of another particle with very, very tiny momentum. You might not notice it. You might not physically notice it because its momentum is so small. Your detector might miss it. But it turns out that the emission of a particle with a very tiny momentum has a singularity associated with it. Or if the particle is emitted very much in the direction collinear with the direction of motion of the particles going out, there's another singularity associated with that. At tree level, that's fine. They're rational functions. They have poles like that, and that's life. But if you start thinking about the quantum corrections, you're forced to integrate over, because it's quantum mechanics, you're forced to integrate over all these things. And you inevitably run into situations where these singularities enter the integration region and you find logarithmic divergences. And then there's a whole story about how one has to deal with those. Right. Those are all, that's right. Those are all covered. I mean, that's all, you know, this part of the physics is, what to do with these infrared divergences is in principle been understood for long time. But actually, part of what makes the story that we're talking about a lot cleaner is that we're able to focus on a nice, perfectly defined mathematical object, which is completely free of these divergences, which is not the, so at tree level we have these rational functions, which are the tree amplitudes. At loop level, it turns out that in this limit, in this planar limit, in this limit as n goes to infinity where we only draw planar diagrams, there's a new rational function in town, which is not the, whose data is not just the external momenta of the particles coming in, but is also the values of the loop momentum variables. So it's a rational function which is the integrand, which you then integrate to get the answer. Okay? Now, the process of integrating to get the answer can have divergences in it, it can have all these subtleties, but we can defer that entire discussion to the very, very end. And there was a nice, well-defined rational function in town No, and actually in this theory, there's also so the ultraviolet renormalization is completely absent in this theory. The only divergences are associated with the fact that they're massless particles, which are infrared ones, which are infrared divergences. Yes, we're just talking about infrared divergences. And even these infrared divergences are absent in the quantity, which is the integrand, not the final integral, but the integrand.
But you have to do the final integral to complete the scattering.
Yeah, so that's right. We know also how to regulate these integrals in a very canonical way. So it's not. I mean, things are completely under control at the level of the integrand, and there's something pretty canonical to do to regulate these logarithmic divergences when you do the integral.
And when you regulate them, then you can after you regulate them, can you remove the regulators or not?
You can remove the regulators if you ask appropriate physical questions. So the sort of quantities that end up being regulator independent, as usual in physics, if you ask a perfectly physical question, you will get a finite answer. But for example, you have to ask the sort of I told you these infrared divergences have to do with the fact that you might emit a particle that was very, very soft, for example, had a very low energy, so the detector might not notice it, right? So what that means physically is that if you have a detector and your detector has some energy resolution, you have to say that I necessarily have to add up all the processes where I emit an arbitrary number of very, very soft particles that are beneath the threshold of my detector, right? It turns out when you add up all of those things together, the divergences that you get, these rational function divergences that you get at tree level, together with the loop divergences at loop level, cancel beautifully, and you get a finite answer. But you get a finite answer that depends on the resolution of the detector, and it's just it's true. It's a fact about it is a fact about the world that.
You're telling me the detector gives you a cutoff?
Yeah, the detector gives you a cutoff, and there's actually two sorts of things that you have to do. That's one of them. And the other one, because there's two kinds of divergences, one when the particle is very soft and the other one when the particle is very much aligned in the direction of motion. You also have to decide, you also have to decide on only accepting, looking inside a cone of a fixed size around the direction of motion of some particle. And add up everything that can happen inside that small cone, and that also regulates the answer and sort of fully removes all of the divergences. But I think for the purpose, I mean that there's a whole story associated with that, and perhaps it would be marvelous if eventually even these sort of subtleties get don't have to be deferred and have a beautiful mathematical interpretation. But for now, I think that there's a set of interesting mathematical objects that are totally well-defined, completely, totally well-defined. Which I think are the things that are at least that are interesting for now. Perhaps the other ones will also have such nice interpretations.
When you do these ladder graphs, not ladder graphs, the planar graphs,
right?
That you sum.
Yes.
So is this in principle summable?
In
other words, is it actually a convergent series?
Is it a convergent series?
Yes.
Yes. Right. Yeah. This is a really important point. That it is in fact at infinite end it is convergent. So one often hears about Feynman perturbation theory. That Feynman perturbation theory is asymptotic. Okay. And as a number of colors. So we had this SUNC gauge theory, right? And one often hears that the Feynman expansion is asymptotic, and it is indeed asymptotic, right? Huh?
Unless you take the limit of n goes to infinity. First.
Right, or if I say it slightly more invariantly, if G is the coupling constant, or G squared is the coupling constant, what we're instructed to do to take this large n limit is send n to infinity, holding G squared n, sometimes called lambda, fixed. So it's G squared times n, which is fixed. And this is sort of easy to motivate because if you have a 1 over g squared, so we conventionally put a 1 over g squared trace f squared there, but it's better to write it like that. So if we write it as n over lambda, then with the n there, all the combinatorics, it gives you a clean expansion in powers of 1 over n. Okay? So that's what a Twift figured out in the 70s, that the Feynman diagrams you get with this normalization have an extra 1 over n for every hole you have in the diagrams.
And planar diagrams you don't have the number singularity,
right? Right. That's right. But the point is that standard Feynman perturbation theory is indeed asymptotic, and that means that once you start talking about effects that are that small, they just can't be predicted anymore. I mean, that's what it means that it's asymptotic. But you see, this is equal to e to the negative n over lambda,
Yes.
and so if you send n to infinity, this is perfectly fine. Okay. This goes to 0. That's right. So there are no non-perturbative effects in this limit, and so that's very powerful. If you knew the entire perturbation series, you could in principle resum it to get the whole answer. Perturbation theory has a finite radius of convergence.
Is that what you do with these?
That's the hope to do with this model. And there are some cases, not for the problems that I'm telling you about, but for other problems, where people have managed to do exactly that. And we do have. There are some results that you can extrapolate and interpolate between weak coupling and arbitrarily strong coupling, and of course you confirm all the sort of general lore. Yeah.
Does this mean that the answer makes sense even for small negative lambda?
The answer makes sense even for small negative lambda, and the reason it does, so that there's this famous old argument due to Freeman for why perturbation theories should be asymptotic. The argument was that if you imagine it's QED, and if you made 1 over g squared negative, then the coefficient, then that means that the energies associated with the photon can become arbitrarily negative. And so there's no cost at all to popping out an electron and a positron pair from the vacuum and just having this runaway process where you create them over and over again. The same process can indeed happen in this theory, but its cost is e to the negative n over lambda. Okay, so I mean, it's just exactly the same argument. It's e to the negative n over lambda, and if you send n to infinity holding lambda fixed, it just doesn't happen. So you can indeed go to small negative lambda. And as I said, there's a number of exact formulas in this theory that are known already. Not for these quantities that are the sort of very physical ones that we like, but well, they're still for pretty physical quantities. The spectrum of the quantum dimensions of all the operators in the theory is essentially a solved problem. I mean, remarkably, solving that problem involves a lot of the same kinds of mathematical structures that I was talking about in my talk. It's just that we seem to be seeing more and more of them when we ask an even more physical question, which is this question of scattering particles from minus infinity, having them go out to plus infinity.
You were telling that the theory was n equals 4 supersymmetry.
Yes.
What is important about those assumptions? With less supersymmetry, nothing would work?
Well,
With some other infinite good?
okay, so the SUN is completely irrelevant. If you send, as long as you send n to infinity, all the information about the group simply disappears, right? So that part isn't important. The n equals 4 is the n equals 4 at the moment is very important simply because it's, in a sense, the simplest quantum field theory in 4 dimensions. It doesn't look like it. You know, the Lagrangian looks like a complicated quantum field theory, but I mean, this is one of many indications that there's something wrong with the Lagrangian. When you write down Lagrangians, it fools you into thinking that some theories are simple and some theories are complicated. You know, you write down a Lagrangian, you think just a theory of a scalar field with a phi to the 4th interaction is the simplest quantum field theory. And that's something like n equals 4 super Yang-Mills, has a ton of fields. Okay, sure, it has a lot of symmetry. Maybe that would make you suspect that there's something good about it. But it sure looks complicated at the level of Lagrangian. But when you look at the actual output of quantum field theory, the actual observables, you know, what you actually compute, the answers, even though the Lagrangian is simple for phi to the 4th theory, the answers are horrible. Whereas the answers are beautiful and simple for n equals 4 super Yang-Mills. So that's one reason for studying it so much.
If I were to do phi
yeah.
to the 4th,
essentially none of the magic that I'm telling you about would actually happen. Right.
And the UN.
Right. Now, of course.
So you're using this extra symmetry.
Yes, absolutely, absolutely. And in fact, not only is it maximally supersymmetric, but what's been discovered in the past number of years is that this theory has an infinite dimensional hidden Yangian symmetry, and that integrable structure seems to be playing a huge role behind the scenes, and part of what we're trying to do is expose that more. So perhaps I can just I don't know what will be useful, but perhaps I can just give a name to the various spaces that things live in and what the variables are and things like that. Would that be useful? So we start off in So I'm just going to do a little bit of just pure kinematics for a little while, and then we're going to end with just a definition of what the object is in the appropriate Twistor space, which is where everything is incredibly nice, and we've trivialized the kinematics as much as possible. And then that's I think where I can then start talking about these Grassmannian structures and associated polytopes that seem to be related in a deep way in a deep and surprising way to this physics. And that's, I think, the place. Well, that was certainly something that you wanted to hear about. So we'll get there shortly. But so we're interested in the scattering of massless particles, gluons. And so the data starts off life being a bunch of four momenta, PA. So these are some zero component and some vector component. So for me here, always A runs from 1 to n, where n is the number of external particles. And there's one more piece of data I need to tell you. These particles have spin. And when they're massless, they have spin 1. But actually, they're massless. So normally, a massive spin 1 particle has 3 polarizations, Sx, Sy, and Sz. But because they're massless and they're zipping around at the speed of light, you can never go to a frame in which they're at rest. So you can never so the only spin degrees of freedom they have are actually helicity, the spin in the direction of motion, or the component of spin in the direction of motion, which can be +1 or -1 because it's a spin 1 particle. So these things, so a gluon either spins in its direction of motion or opposite to its direction of motion, or some linear combination of those two, but there's no state which has 0 spin in the direction of motion. So there's two, the sort of Hilbert space of a massless gluon is labeled by 2 spin states, not 3 spin states. And this is said in a more fancy way. I mean, this is what Wigner figured out in the 30s in looking at unitary representations of the Poincare group. That unitary representations of the Poincare group for massive particles are labeled by spin, are labeled by the little group, which is SO3 for massive particles. But for massless particles, the little group is different. It's the 2-dimensional Euclidean group. And in fact, you're forced to live at the origin in that 2-dimensional space, so it's really only labeled by helicity. So it's really a consequence of unitarity and quantum mechanics. But there's a simple intuitive argument for it. It's moving around at the speed of light. I mean, one way you can conclude that a massive spin 1 particle should have 3 degrees of freedom, should have 3 spins, is you just go to its rest frame, and in its rest frame you perform rotations. And if it was pointing on the z-axis, you could make it point in any of the other axes. So you had better have all those states available. But when the particle is massless, you can't boost to the frame where it's at rest. This argument fails, and in fact you only have 2 degrees of freedom. So that means to specify fully the external data, I also have to give a helicity for these particles. Where each of these h's is plus or minus 1. So at the moment, we have something that we call Mn, which depends on the PA and the helicity A. Okay. Now,
No, so
yeah.
this is just particle one has to think to attach to the gauge field itself.
Yes. Sorry. Yes. So these are the particles associated with the gauge field itself. Right. These are. So I mean, if this was QED, these would be photons. In non-abelian gauge theories, these would be the gluons. Right.
There I was confused because I was thinking that to speak of scattering, one needs to have some kind of asymptotic free field.
Right.
And here, non-abelian gauge.
This is where it's important that this theory is conformal, actually. So because it's conformal, it doesn't have this property that QCD has, that eventually there's confinement and the gluons get confined. Here things really can escape to infinity. There's no so really the asymptotic states actually do exist. So you can talk about this.
Is there a classical picture from it in terms of what the
Yes, that's right. For example, these tree amplitudes correspond, are associated with some nonlinear solutions of the classical equations, where which have in fact, what the tree amplitudes are roughly speaking, if you imagine finding a solution of the classical equations, I mean, literally some a mu a of x, some classical solution, right? And let's say that these asymptotes to a mu of a x as x goes to infinity goes to a sum of a bunch of plane waves. So epsilon mu a e to the I, sorry, different a's. This is the vector gauge field. This is the it's the matrix valued gauge field. Okay, so let me just so let's say it goes to some epsilon. It goes some sum over a. These are now the particles epsilon mu a e to the I pa dot x with something that takes up the some matrix M in the color space MA. Okay, so this is just saying that we're sending in things which are asymptotically right, which are plane waves, but then they're going to interact in some way. Then the scattering amplitude can actually be thought of as the classical action evaluated on the solution. Okay. So it has more it has less information in it than just the classical than the full solution. But if you evaluate the classical action on the solution, and now the solution is labeled by this data that tells you what it's doing at infinity, that is actually equal to the tree amplitude. This turns out not to be a very useful formula for doing any sorts of calculations, but it is true. Yeah.
Terminology. The action means what you integrate for the Lagrangian.
Right. Exactly. That's right. So this just means that the integral of the Lagrangian on this classical action is right. So tree amplitudes are very closely related to solutions of the classical equations of motion. And right. Oh no, we'll be considering them. We'll be considering all of them in a moment. I'm just talking about gluons, but yeah, we'll talk about all of them in a moment. So okay. So what we then have is so there's just a few steps that help. There are a number of steps that just help us talk about this kinematics in an even simpler way. One of them is that when we deal with these massless particles, we have this restriction that p0 squared is equal to p squared, which is an annoying quadratic constraint to have floating around. So one thing that we do immediately is we trade. So if we if we associate it with p mu, is this 2 by 2 matrix. This is something that I'm sure you all know incredibly well. So so we can call this matrix PAA dot. So where now this A runs from 1 to 2, A dot runs from 1 to 2, and the determinant of P is equal to, evidently, is equal to P dotted, the vector P dotted into itself, which is just P0 squared minus P vector squared. So if this is a massless particle, this determinant is equal to 0. And so we can conclude that this 2 by 2 matrix has rank 1. So we can write PAA dot is equal to some lambda A, some lambda tilde A dot.
I remember you had said you were complexifying.
Yes, and now everything is actually going to be, everything is complexified.
So
And
this is telling that complexified Lorentz space is obtained from a tensor product of two
Yes,
two-dimensional space.
exactly,
You
right.
look only at decomposable.
Right, exactly, precisely. And actually, the complexified Lorentz group is then SL2 cross SL2, where this is the SL2 that acts on these guys, and that's the SL2 that acts on those guys. So this is very nice now. Now, if I just give you unconstrained lambdas and lambda tildes, they give me something which is massless directly, right? Of course, the lambdas and lambda tildes are not uniquely defined because I can rescale lambda by T lambda and lambda tilde by T inverse lambda tilde, and that leaves P invariant. That's actually good because the homogeneity of because the amplitude has got to behave homogeneously under these rescalings, and the degree of homogeneity tells you what the helicity of the particle is. Okay. So what we find is that, so if I give you an amplitude now that depends on lambda A, lambda tilde A, and the helicity, then it must be that Mn of, if I rescale that this is just a convention, T to the negative 2h, Mn of lambda, lambda tilde, and h. Okay? So the redundancy in T is actually telling you the amplitudes have to be homogeneous functions of the lambdas and the lambda tildes, and the degree of homogeneity tells you the spin of the helicity of the particle.
Are you thinking that this combination P and some vector in this
Yes.
two-dimensional space is the same as to give actually lambda and lambda tilde?
Right. If you specify lambda and lambda tilde, then now we're automatically talking about massless particles. And furthermore, if we were talking about functions of appropriate homogeneity, then we even know what helicities we're talking about. So all the information about both the masslessness and the helicity is encoded in this function of lambda and lambda tilde. So for instance, just to give an example, and I should have said that the invariants that we can build out of the lambdas and lambda tildes are simply just contracting them with epsilon symbols. So if I have a lambda 1 and a lambda 2, I can have something that I can call lambda 1, lambda 2, which is just epsilon alpha beta, lambda 1 alpha, lambda 2 beta. And similarly, there's a lambda tilde 1, lambda tilde 2, which is epsilon. Oops, I was calling these different variables before. Lambda 1a, lambda 2b, a dot, b dot, lambda tilde 1a, lambda tilde 2, b dot. So the things that are invariant under SL2 cross SL2 are just these simple bilinears. Yeah, that's all. Exactly. Just the trivial volume forms on the two-dimensional space.
Those constitute Lorentz metric, in fact.
Yeah, sorry? Yes, that's right. Right. So, so just to give an example, if I write down, if I write down an object like this for 4 particles, which happens to be a physically important amplitude.
Would you say what that shorthand means?
Yeah, the shorthand means yeah. So right, So the shorthand 1, 2 is exactly the contraction lambda 1, lambda 2. Okay, A, B. So every time we have these angle brackets, the angle brackets involve the lambdas. The square brackets, if I write them down, involve lambda tildes. And when I write down 1, 3, so 1, 3 there is a stand-in. So this is supposed to be an amplitude for a 4-particle scattering. Okay? So the data is lambda 1, lambda tilde 1, lambda 2, lambda tilde 2, 3, and 4. And so 1, 3 is just a contraction, epsilon AB, lambda 1A, lambda 3B, for example. Okay? Right.
So, wait, so those are 8 complex numbers or 8 elements of it?
Sorry,
each
lambda is 4 complex numbers, is a 2 vector. Each lambda is a 2-dimensional vector.
Is one of those references?
Yeah, so
Associated as the 2 copies of SL2.
that's right. Each lambda, so the lambdas are associated with the left copy of SL2, and the lambda tildes with the right copy of SL2. Okay, so right. So let me write this down here again. So remember, each P A dot, this 2 by 2 matrix, we wrote as a lambda A, lambda tilde A dot. So this is a 2D complex vector. That's another one. And we have, the Lorentz group is SL2 acting on the lambdas cross SL2 acting on lambda tildes. Okay.
This is not really any kind of, I thought it was a correlation function. This is without any kind of interaction with the Lagrangian, right?
Sorry?
This doesn't involve any interaction with the Lagrangian. Do I understand this is just a rational function?
This is just a rational function. This is just a rational function.
So you haven't taken any expectation or any averaging or anything?
No, well, this is the result of what happens. I mean, you would get to this result if you summed Feynman diagrams that had gluons coming in and going out. And then in this case, you would add up, I mean, yeah. These are only tree diagrams, yes. So I'm just talking about. So this is actually what a tree amplitude, a piece of the tree amplitude. It's not a full amplitude. It's just a piece of the tree amplitude. Yeah.
It's explicitly given by this expression.
Yes. So here's some explicit expression, even before telling you what it corresponds to physically.
So it's a function of 16 complex variables?
It's a function of 16 complex variables. Yes, it is a function of 16 complex variables.
And there's
yeah.
no implicit summation.
There's no implicit summation. Nothing. That's right. Everything is completely explicit. I just wanted to show you what one of these things looks like, right? And furthermore, we can actually see what the helicities of these various particles are just by looking at the homogeneity of this equation, right? So if I rescale lambda 1 goes to T1 lambda 1, there's 4 1s upstairs, 2 downstairs, so this goes like T1 squared. And therefore, according to that formula, that means that particle 1 has helicity minus 1. Okay? So particles 1 and 3 have helicity minus 1, particles 2 and 4 have helicity plus 1. Okay? So the degree of homogeneity here tells you, really, all by itself, that we're talking about that scattering amplitude. Okay? 1 minus, 2 plus, 3 minus, 4 plus. Okay? It also tells you that you cannot take this and add it to another guy. I mean, so this is a nonsense formula with the same thing. These can't be added to each other because they have different homogeneities under this rescaling. Okay, the amplitude. Sorry.
Why is that bad?
It's bad because Because I mean, I could have said I could have said it. I could have said it more properly earlier on. The fact that this rescaling leaves the massless particle invariant, but it does something to the lambdas and lambda tildes, right? Okay, what it does is actually precisely a reflection of the action of the little group. That's exactly how. So it actually has to correctly represent the little group on the amplitude, which is why it must have that homogeneity. If it doesn't have that homogeneity, then we're talking about something which is not properly representing the asymmetries, right? Yes, yes, absolutely, right, right, exactly. Okay, all right, now. Yes, and in a moment we're going to make it even nicer. In a moment we're going to make it, see, something which is annoying here is that these things clearly want to be projective, but we can't just, you know, we can't just say that, lambda and lambda tilde both live in CP1. We can't do that because there's this stupid, one goes one way or the other goes the other way. So we're going to introduce better variables in a second, where we can say that but still, there's still a three-dimensional space which is being spanned by these guys up to the rescaling. So when in a moment we introduce Twistor variables, we'll be able to comfortably talk about CP3. Okay, and that's one of many things that is going to make life easier. Oh, very good. Thank you. So let me now say something about the color. So right, no, it hasn't ended so far, but and it won't ever again after this slide, after this Blackboard slide. Yeah, sorry.
Because you just got to deal with planar graphs.
Right. We're dealing with planar graphs, and all the dependence on the color we can strip out. So let me just write down the formula. Okay. So really, I told you the amplitude is a function of momenta and helicities, but really it's a gauge theory. So you should have complained right at the start. Isn't it also a function of the color indices? It is. Okay. However, and this is the important point, whether it's planar or not, we can always organize the dependence on the color indices as a sum of traces over the generators in any representation we like. Let's say the adjoint representation. So we can have this as a sum over things that look like trace TA1 to TAN times something now that only depends on 1, 2 up to n, and no longer has any dependence on any dependence on the color indices. Okay. Now, so what we really do is so for every this depends on A1 and AN. For every permutation of the A1 and the AN, right, we write down a color factor like this, and there's the associated this associated color list or so-called color stripped function on the right. Okay, so but that has a nice consequence. Yeah. Yeah. So it's a sum over permutations. So so let me write it like this. It's a sum over. Let me be very, very explicit. Okay. It's a sum over, yeah, so this is M of, it's a sum over permutations of the A's, of A of P1 up to A of Pn, M of P1, this is the permutation of 1 up to the permutation of n. Yeah. Okay. So this is the only piece that depends on color, and here we have something that only depends on the helicities and the momenta of the particles. So. But
you don't take permutation.
Sorry?
Those AP1, APN, it's just a permutation.
They're just permutations. That's right. So we sum over. You see, you would expect permutations to be important because these particles are bosons, and so we should we'll be summing over all possible. We will necessarily be summing over all permutations of these guys. It's just that the color structure comes out in factors that can be organized in terms of these traces and everything else. Now, in a general theory, if it was,
Why only the obvious representation?
oh, it doesn't matter. It doesn't matter. Pick any representation you like. Then pick any representation. Yeah. Just for simplicity, let's just use the adjoint representation.
But
Okay.
I don't see how it's compatible using one and the other. If you take the tensor square, you get the square of the.
Oh, so here, but here we're only talking about gluons in the adjoint representation. Okay. So since there's a uniform, everyone's in the same representation. I could do this in the adjoint representation. Never mind what I said. Let's just say everything is in the adjoint representation. Okay. So just to make life simpler. If I chose another representation, then I would have to rescale what I mean by these guys, by the appropriate by some appropriate factors. If I have many different kinds of particles, quarks, gluons, other kind of particles, then you'd have different. Then you really have to keep track of the different kinds of traces that are involved. But just to make life simple, we're only talking about particles in the adjoint representation. Now, in a typical, if we're not at large n, then we can have multi-trace terms as well, and more traces. But all of these things come in with powers of 1 over n, I mean that they're not generated by planar diagrams, and so we can forget about all of them. So that's why life is particularly simple, and the object that we focus on is the m that just depends on p1 up to pn. But this object should have a nice cyclic property. It should have some cyclic symmetry. The cyclic symmetry is very, very important.
Because of the color, you have lost the full symmetry.
Yes, exactly. Because of the color, exactly. We started off life with a full Bose symmetry, but because we've stripped off the overall color factors, the thing that we're left with only has a cyclic symmetry. It's a cyclic symmetry of the trace. Okay. All right. So let's keep going. But now this ordering is actually this cyclic symmetry is very important because it means that we should really think about our particles as being ordered around a circle. Okay. So we really have something that depends on 1, 2, 3, 4, up to n. Okay. Sorry? If one reverses the order. Yeah, I mean cycling. Cycling forward, or you mean flipping. Flipping are also sometimes symmetries. It's related to it's not always a symmetry. I think only the cyclic invariance is always a symmetry. Yeah. Okay. Now, we just want to make our life even simpler. So right now, we're dealing with functions of lambda and lambda tilde and helicities. We'll deal with the helicities just at the end of this discussion. Even having the helicities around is a little annoying. It's annoying to have these plus and minus labels on everything. That's one of the motivations of supersymmetry. Supersymmetry is going to allow us, we add a lot more particles. We add a lot more particles. Maybe I'll deal with that now. We add a lot more particles. So we have this negative helicity gluon and this positive helicity gluon. We have one of each. With supersymmetry, we add four. So the helicity is -1. So this axis is going up is helicity. And here we have one of them and one of them for standard Yang-Mills. When you add supersymmetry, we add 4 of them, which have helicity -0.5. 6 that have helicity 0, and 4 that have helicity +0.5. So at first, it looks like we're making our life a lot more complicated because we're adding lots and lots of extra particles. But there's really a point in life of adding all these particles, which is it allows us to unify all of these things into a single multiplet, okay? A single supermultiplet. And because of that, we actually label, instead of labeling the particles by labeling their helicity, we label them by there are generators Q, A, and Q tilde A dot, which are supercharges. There's actually 4 of them. So that's what makes it n equals 4 super-Yang mills. So I runs from 1 to 4. A runs from 1 to 2. These are the same SL2 indices we were talking about before. Okay. And so using these 4 Grassmann generators, we can start at the bottom. And for example, so the bottom is annihilated, let's say, by Q. But we can use Q tildes to go all the way to the top. We can use, every time I act with a Q tilde, it increases the spin by half. Because it's Grassmann, I can't square it. But I can use Q tilde 1, Q tilde 2, Q tilde 3, Q tilde 4. Those are the different I components to take me from negative helicity to positive helicity, or the other way around. So all these things are, yeah.
That whole thing is an exterior algebra.
The whole thing is an exterior algebra, absolutely, right.
And where did the number 4 come from?
The number 4, well, I mean, the number 4 is the number of supersymmetries, well, if you're trying to go from negative helicity 1 to positive helicity 1, then you want to do it with 4. If you can only do it in steps and a half, there's no other choice. And this corresponds to maximal supersymmetry for Yang-Mills theories. So particles associated with spin 1. If you do this with gravity, so you'd start with helicity -2, and you want to get all the way up to helicity +2, then you have to have 8 of these supercharges, and that's the maximally supersymmetric gravitational theory. That's n equals 8 supergravity. This is n equals 4 super Yang-Mills. But that number 4 really came from the only, right. And what this means is that instead of labeling the states by helicity, like +1 or -0.5 or whatever, it's better to label the states so they're eigenstates of one or the other of these operators. They don't commute with each other, so they have an anti-commutation relation, which is QAI, Q tilde A dot J is delta IJ, and then this is actually precisely the momentum, PA A dot. So they don't commute, but you can diagonalize one or you can diagonalize the other. And the states that diagonalize them are, we conventionally label by some Grassmann variable. Well, let me call it eta tilde for simplicity, just because later I'll be using eta a lot. But anyway, eta tilde for simplicity, which is, for example, just to be, I mean, it's just the exponential. It's just, I mean, roughly is e to the eta tilde q, for example, q tilde acting on the negative helicity state, which explicitly is just some combination, minus plus eta tilde I times the -0.5 I. You see there are 4 of these fermions. There's 4 eta tildes, so I can have that. There are 6 scalars. So there's a 1/2 factorial, 1/3 factorial, eta I, eta tilde I, eta tilde j, eta tilde k, times the +0.5 fermions. Anyway, it's clear what I'm doing. Plus the eta tilde to the 4th on the positive helicity gluon. Okay? And these are nice. These are nice states on which supersymmetry acts nicely. Okay? This state is an eigenstate of Q. Okay? So Q on eta tilde is eta tilde on, yeah. So yeah. Q on eta tilde so QAI on eta tilde is in fact eta tilde I lambda A eta tilde. Okay, so it's you're diagonalizing the eigenstates. So that means that we can now, instead of having this somewhat annoying plus or minus helicity label floating around, now the amplitudes are nicely functions of lambdas, lambda tildes, and eta tildes. And so everything is smooth here. Everything is smooth. We have we have bosonic and Grassmann variables, but there's no, yeah. Eta is a Grassmann variable, so it's so there are 4 of them. So any given, there are 4 of them. I runs from 1 to 4, and so
momentum dependent?
They're not momentum dependent. No, they're just they're a replacement for the helicity label.
Oh.
They're a replacement for the helicity label. You see, if I give you that function of eta tilde, if you want to extract out of the amplitude the one for which that particle has helicity -1, you just set eta tilde to 0. If you want to extract from it the component where I mean, it's like a generating function, right? If you want to extract the component which has helicity -half, you differentiate with respect to eta tilde and set everything else equal to 0, and so on. Okay? So you just use this, but this is a much more symmetrical way of combining everyone. It's a fantastic bookkeeping device, right? And in fact, this is from the point of view of these amplitudes, it's incredibly natural to introduce supersymmetry for this reason alone. Even if we'd never heard of any of the other motivations for it, this bookkeeping device is incredibly powerful and useful. And it's just it just allows us to get going, having as little baggage as possible in describing what we're doing. So let me finish by right, lambda A. So A is a particle label. Okay? So lambda A is in one SL2 of Lorentz, right?
So A, that's the vertical.
Yes, A is a particle label. Sorry, yeah. Then we have lambda tilde A, which is an A dot, and we have eta tilde A, which has this. So this is SL2, and this and I is the SUSY is acted on by the supersymmetry.
The A's just label the incoming and outgoing.
Yeah, and in fact, we've just declared that everything is incoming. So we treat everything symmetrically. Just some of the momenta have. So instead of saying there's particles incoming and outgoing, we say everything is incoming, but the ones that are outgoing we treat with are the ones that have negative energy. Say, okay. So yeah.
And the big N is always sent to infinity, so we never have to worry about that.
Yeah, that's right. We never talk about the big N again. So everything about the color group is now got put into the fact that we're dealing with this object that depends on 1 to n. And now in this form, finally in this form, this object is literally cyclically invariant. Okay, so literally this, so m of I mean, if you just shift all the labels by 1, you get exactly the same function back. The A's, the little a labels. Okay. So.
What does it mean physically that all the particles have a cyclic order?
Right. So the thing which gave them the cyclic ordering is the color. So if I sort of draw, it's maybe clearer if I draw a sort of picture. So because the gluons are in an adjoint representation, it's useful to use if you just want to follow what the color indices are doing. It's useful to introduce a double line notation where you right. So where you think about the adjoint as being an n times n bar, this is telling you the n and the n bar indices. Okay, so the reason why a cyclic ordering is enforced on the particles is that we have to draw planar diagrams. Okay, so if this is particle 1, then right. Then I can only draw diagrams like this, and any diagram I draw that would not be cyclically ordered forces a line, one line to go.
Right?
Sorry? Yes, exactly, precisely. Yeah, right. So it's the planarity which is enforcing the cyclic structure on the answer, and the cyclic structure is a gigantic part of this story. Yes. Very good. Yeah, and here it's turned already into a simpler statement that mn of lambda t lambda T inverse lambda tilde and T inverse eta tilde is just T to the minus 2, period, Mn of lambda, lambda tilde, and eta tilde. Okay? So it's already a much simpler statement, reflecting the fact that we've shoved all the information about the helicities into the eta tildes. Okay? In a moment, it's going to get simpler still, but this is the statement about homogeneity now.
So for instance, if I take eta to be 0, then you recover what you were telling that you had.
If I take components of eta to be 0, then I can reflect the previous statement about gluons. But you take any component you like, and you'll get the correct homogeneity for those particular particles. Okay. So now let's actually just go back to the bosonic part and finish introducing variables that are as simple as possible to talk about the scattering amplitudes. So because we have the cyclic ordering, it's natural to draw the momenta one after another on a sheet of paper like this. So they close into a closed polygon. Okay? They may cross itself. It can do all sorts of things. Right? Yeah. Sorry? This is in some four-dimensional space, right? Because the four momenta are each four-dimensional. So this is in some four-dimensional space. We've introduced a new. So let me just be very, very clear. So we have our ordinary space-time, usual space-time. Okay. Sort of conjugate to our usual space-time is momentum space. So a lot of the discussion we've just been having has been in momentum space. And now we're actually introducing a new space-time altogether. We're introducing another space, which is the space in which this closed polygon lives. Okay? So let me. So I'm gonna use variables x to describe this space, but please don't confuse x with standard space-time. Okay? Maybe just not to confuse it. Let me call it y. Okay? So I've introduced a new space where the momentum of particle A is just the difference of is ya plus 1 minus ya. Okay. So
It's not unique.
no, it's not unique. Very good, very good. It isn't unique. I can just translate everything, and I'll have exactly the same p's back. So that sort of redundancy is there and is very useful, and we'll talk about how it fits into a much bigger symmetry group in a moment. Okay. Okay. All right. So again, we're still trying to unconstrain our variables. We started with p's. They were massless, so we introduced the lambdas and lambda tildes. But still, they satisfy this quadratic. They still satisfy constraints that all the p's have got to add up to 0. So we're trying to even remove that constraint. We want to say, just specify a bunch of points in this space y, which close into a closed polygon. And then that'll guarantee that momentum is conserved. That'll guarantee that some of the PAs adds up to 0. But still, we have to enforce that the edges are null. That all the edges, all the edges are null. So it's still a constrained polygon. It's a null polygon in this space. Okay. Yeah, that's right. It means that the edges are all light-like. The edges are null. Okay. That's right. So if you like, I can say each one of the edges are lambda tildes, and that would guarantee that it's null. But there's still a constraint that needs to be satisfied for them all to close up with each other. Or I could say, forget about lambda tilde. Just give me a bunch of points. That'll guarantee that momentum is conserved. But I have to enforce by hand that the edges are null. So now what we're going to do is finally introduce a set of completely unconstrained variables that lets us talk about the kinematics in the simplest possible way.
Are these p's real or complex?
They're complex. Everything is complex. Everything is complex. And this is done by using Twistor space. Now, actually, so Penrose's Twistor space was supposed to be associated with the usual space-time. So this is the original Twistor space. Yeah, I will explain explicitly what it is in a second. But just to avoid a terminological confusion, I mean, these things are all very closely related, but they're not identical things. So Twistor space is a very useful thing. It makes conformal symmetries manifest. It does all sorts of wonderful things. But Penrose's original idea was associated with the usual space-time. The Twistor space that we're talking about is going to be associated with this space-time, okay? Not the usual space-time. So it has a different name. It's called momentum Twistor space. Okay. So that's where we're about to go. Okay.
Parameterization allows it sort of automatically enforces this group.
Sorry? Yeah. We're going to come up. It's first of all purely kinematically. It's a parameterization where I finally give you completely unconstrained variables, and they just build up correctly a kinematics, okay? And they make manifest many of the symmetries of the theory. So there's incredibly useful coordinates, right? Now, I don't know the easiest way of making this. I mean, this is related. Well, this is something you all know extremely well. It's related to the fact that G24 is the same as space-time is the same as the four-dimensional space. Let me just go through it. Okay, so the idea behind Twistor space. Let me actually go back and even. I mean, since these sort of kinematical things are exactly the same in both spaces. Everything I'm saying is just true for a general Lorentzian space. So if you take a general four-dimensional Lorentzian space, the idea is not to focus on points in space-time as sort of primary objects, but as null lines in complex null lines in space-times as the fundamental objects. Okay, so the idea is to look at complex null lines. Now, to specify a complex null line in space-time, you can easily convince yourself that, well, if I look at the set of solutions to this equation, let me write it like this. If I look at the set of solutions to the equations, mu a dot minus x a dot lambda a, sorry, yeah, lambda a equals 0. Okay, so if you give me two spinners, two complex spinners, lambda and the lambda tilde, and I look at all the solutions to this equation, all the x's that satisfy that equation lie on a null line. It's easy to see that the line is null if you subtract this equation for the same mu and lambda, you look at one solution, x1, and another solution with x2. And if we subtract them, we discover that x1 minus x2 annihilates lambda. And so x1 minus x2, the determinant of x1 minus x2 is 0. And so x1 minus x2 are null separated. Okay? So all the solutions of this equation lie on a null line. So therefore, I then have a correspondence between a null line. I have a correspondence between a null line and this four-dimensional object. I can group the mu and the lambda into a four-dimensional object, give it a name, z. So if I take this vector in C4, the vector in C4 is associated with a null line in the Lorentzian spacetime. Of course, I can multiply that equation by any constant, and it doesn't change the null line. So this should really be so Z and TZ are to be identified. So really, Z lives in CP3. So a point in CP3 is in one-to-one correspondence with null lines in spacetime. That's the basic equivalence. Conversely, if you take yeah, these are
how many null lines?
okay. So this is actually an important point. This is a particular complexification of the space of null lines in Minkowski space. So
What about null lines in the real space?
huh? No, this is so let's
But it's
yeah.
not
So
time you don't go through the origin.
sorry.
You don't go through the origin. You take them. You take this line and also that one.
No, that's right. Those are all. So if you have a line and another line, they each correspond to a different value of mu and lambda. No, but let me say a little more precisely what's going on. If we look at the space of null lines in real Minkowski space, that's a 5-dimensional space. Okay? So you can think about you take your laser beam here, you point it somewhere in the celestial sphere, so there's 2 angular coordinates, and then there's a 3-dimensional vector that specifies its position relative to some origin. So the space of null lines in 5-dimensional Minkowski spaces, in 4-dimensional Minkowski space, real null lines is 5 real dimensional. If you naively complexified it, it would be 5 complex dimensional, a 10 real dimensional space. This is not the naive complexification. Okay? This is a specific complexification. Which associates specific null lines in complexified Minkowski space with points in CP3. Well, I mean, do you understand that? Do you agree that this is a null line in Minkowski space?
For me,
What I know is
Right.
in
Yeah.
Lorentz space. I don't understand.
Sorry?
For me, this was a story in Lorentz space.
Yes, this is a story in Lorentz space.
I don't
And-
understand how you go to Minkowski. So this is whether there is an origin or not. Here we have just mu and lambda. But
No, oh, sorry, but the x's are to be thought of as points in Minkowski space. So the xAA dot are this is a 2x2 matrix, and I can read off from it an x0, x1, x2, x3. so I read off from that points in Minkowski space. Okay. So the set of all the solutions to this equation gives me a complex line in Minkowski space. Yes.
No, I don't understand. So CP3 has complex dimensions 3.
Right.
The set of all light lines in the complexified Minkowski space has dimension 5. So I just
It isn't all. It isn't all. This is what I'm saying. Right. It's the ones that satisfy this equation. Okay. It's a subset of them. It isn't all, indeed, because of this reason. No. So it's a subset of all complex null lines in Minkowski space. However, it contains all real lines in Minkowski space. Okay. And it's a particular complexification of all real lines in Minkowski space. Okay.
So it is some complex 3-dimensional set of lines which contains all 5-dimensional real 5-dimensional
Yes.
space of Minkowski lines.
That's right. That's right. So that's why I said it's a particular complexification of the space of lines, because indeed the set of all complex lines in Minkowski space is 10 real dimensional. This is 6 real dimensional, 3 complex dimensional. But it's this particular one. I'm telling you which one it is. If you give a mu and a lambda, you solve all the x's that satisfy this equation. That specifies a complex null line in Minkowski space. This is defined up to rescaling. So a point in CP3 specifies for you some null line in Minkowski space. Okay. Now, why is this nice? I mean, what's good about this? What's good about this is that the action of whenever we have massless particles around, we have a conformal symmetry that acts on them. the theory is conformally invariant. So the full conformal group has translations, Lorentz transformations, rotations, translations, rotations, as well as the special conformal transformations. And in the normal way we talk about these things, these three basic symmetries are generated differently. So they're not treated on an equal footing. For example, inversions are very nonlinear, right? You know, x goes to x over x squared is a very nonlinear transformation, whereas Lorentz is treated, Lorentz and rotations are treated linearly. So it's a nice idea to treat all the symmetries on an equal footing and to linearize all of them as much as you possibly can. And you see, these variables do. So on these variables, on this four-dimensional vector, the full four-dimensional complexified four-dimensional conformal group just acts as SL4. So the full conformal group is just SL4 acting on these Z's. So the SL2 cross SL2 is obvious, the upper and the lower blocks. So the SL2 cross SL2 of Lorentz is obvious. But you can see, for example, inversions are obvious. If you say x goes to x over x squared, that just interchanges mu and lambda in this equation. Okay? So the inversions are just a trivial linear transformation that interchanges these two guys with each other. And so in fact, the upper 2x2 block is translations, and the lower 2x2 block are the special conformal transformations, and they all beautifully group up into SL4. So these are the variables on which the conformal symmetry acts as nicely as possible.
So conformal means conformal with respect to the Minkowski.
That's right, exactly. So it's conformal with respect to the original X space, right? But the conformal transformations act as SL4 on these variables. So that's one of the really nice things about them.
Equals SO6.
Yes, SL4 equals SO6, right? Yeah. Yeah. Okay, so this was the first basic piece of the equivalence that these null lines in Minkowski space. Yeah, I should have perhaps said these special null lines in Minkowski space. SL4, I mean, complexified, SL4 equals SO6, right?
Equals SO6, yes, right.
Right. Right. Now, something else you can do is take a pair of points in Twistor space. A pair of points in Twistor space, each is associated with a complex line, and these two complex lines will generically intersect at a point. Yeah.
Can you just return back to
Yes,
the
yes.
situation? Because if you just consider all like lines in
Yes.
the complexified Minkowski space, this partial flex point in CP3 and plane in CP3 is contains this point.
Right.
And so it seems that you're saying that you probably have something like Hermitian form in C4, which you were using, or some kind of real structure which you didn't.
There is a real structure which I haven't told you yet. There's a real structure that tells you what the right.
If you
Right.
put this real structure, then you can say if you have a point, you can take the dual of this point with respect to this real structure, and this specifies your the line.
Yes, yes, absolutely, absolutely.
But
Yeah.
then the group SL4, if you do have this real structure, the group SL4 cannot be the group.
No, that's right. So this is the complexified conformal symmetry. The real conformal symmetry, which leaves this Hermitian form invariant, is SU2, 2, right? Which is the conformal group. I'm trying as much as possible to talk about to deal with the complexified situation because everything we're doing is very holomorphic, and we can defer dealing with these reality issues very late in the discussion, which is why I didn't want to get into it right away. But yeah. I mean, in fact, the whole story is that there's a CP3. Then there is a real form which is in some basis it's 1, -1, and it leaves an SU2, 2 subgroup of the SL4 invariant. That picks out a 5-dimensional subspace of the whole CP3 And it really divides the CP3 into two halves. And there's a sort of upper half and the lower half, and they all have names. Anyway, but we can defer talking about that for a little while. So the second part of the equivalence is that if you take 2 points in the Twistor space, they specify, so there's a line associated with them in this CP3. This is actually associated with a point in space-time. So a line in space-time is a point in Twistor space. A line in Twistor space is a point in space-time. And we can see that, again, we can see that very explicitly because we can see that very explicitly if this is a point A and B, then I'm looking for a solution to mu A minus x lambda A equals 0, suppressing the indices here. Mu B minus x lambda B equals 0. And you can just solve for the x. So x is something like mu A lambda B minus mu B lambda A over AB. Lambda A, lambda B explicitly. So you can easily solve these two equations, and you find an x. And because I can do any 2x2 linear transformation on these equations and not change them, then this point x doesn't depend on A and B except through the line AB in Twistor space that they specify. So there's a correspondence between a line in Twistor space and a point in space-time. Okay, and that's also the same as the correspondence between space-time and G2, 4. Okay, so instead of thinking about the lines in CP3, I can think about 2 planes in 4 dimensions. Okay. Now, so what this really does is it makes we treat all the symmetries on an equal footing, and they're very, very useful. They're very useful variables. But what it means concretely is we can now go back to our problem and really totally solve it now. We're going to now look at what this polygon in the y space, or the space-time, what this polygon in space-time looks like in Twistor space. Okay, so this point, oh, sorry, I should have said maybe obvious things up here. It's of course also very nice that the full conformal group is SL4 and acts linearly over there, because then all of conformal geometry just turns into simple projective geometry in CP3. So for instance, if you have 2 points x and y in space-time and they're null separated from each other, that means that the corresponding lines in Twistor space intersect. So the only projective thing it could mean. Okay, so if we take this picture, let's say we take the point y1, y2. So y1 corresponds to some line in the associated Twistor space. y2 corresponds to another line. But because y1 and y2 are null separated from each other, there's the line that's associated with y2. y3 is associated with another one, and so on. And so this picture of a null polygon in y space turns in Twistor space to a picture where you have lines, one intersecting the next. And that means that I can actually fully specify this picture just by giving a list of the intersection points. Right? So I can just call that Z1, Z2, Z3, Z4, up to Zn. Okay. But now this is incredibly useful because, yeah.
So
This is in CP3. This is a picture of lines in CP3, right. Yeah.
May I ask you a pedantic question?
Yes.
So this y's, as you explained,
Yes.
they are not defined literally. They're defined after a common shift by a vector.
Yes, that's right.
But when you put this picture with z's, you kind of specify this y's literally.
Well, so the point is the following. Pick any y's you like. Okay, fix the Fix the shift, right? It's going to turn out, it's going, you see, it's going to turn out that the amplitudes are actually invariant not only under these translations. The translations, they trivially better be invariant under them because that's just meaningless. I mean, that's just, however, a little bit remarkably, that trivial, meaningless translation, together with the whole rest of the conformal group, actually it leaves the amplitude invariant. So this redundancy doesn't matter because the amplitudes are actually conformally invariant under these conformal transformations. Okay? But it is kind of subtle. It is sort of interesting how it works. You start off with these variables with just a redundancy that had better go away. And it goes away because the amplitudes have a big symmetry. They have a big symmetry under full conformal transformations in the space that contains these translations amongst everything else.
What happened to the helicity?
Sorry?
What happened to this eta?
Oh, to the eta, I haven't said. For the moment, we've been ignoring etas, and I'll come back and tell you what happens with the etas at the very end. This is just trying to come up with. This is just trying to come up with some just bosonic variables that are null and satisfy momentum conservation automatically. And so you see, we've done it. Okay. If I just specify a collection of z's, I'm done. If I specify a collection of z1 up to zn, from these I can reconstruct a bunch of y1 up to yn, where ya minus ya plus 1 minus ya are null. Okay? And from there I can reconstruct, then reconstruct a lambda and a lambda tilde. Okay? Because ya minus ya plus 1 up to the t and up of course, so the t and the t tilde. Okay? Actually, let's come to the t and well, so let me first write down just the explicit formula. Okay? So the explicit formula is simply the following. If you take za, so it's mu a and lambda a.
Excuse me, Nima,
Yeah.
I have to go. I have
Oh,
a
okay.
5 o'clock meeting.
Oh.
In case they don't show, I'll be back.
Okay. So then we have that the lambda a's at the end are just these lambda a's, so there's nothing to say there. But the lambda tilde a's are the following nice object. They're a minus 1a mu a plus 1 plus a plus 1 a minus 1 mu a plus a plus 1 mu a minus 1 over a minus 1 a plus 1. So I could have, if you like, could have skipped the entire picture and everything and just written down this formula as an explicit solution to the problem we're interested in. If I hand you random mu's and lambdas, so these angle brackets are just contractions made out of the lambdas, then this formula guarantees that the sum of lambda a lambda tilde a is equal to 0. Okay? And you can check that as a very simple algebraic exercise. But this is really reflecting this nice picture in Twistor space. Okay?
So to get the lambda, you need not just a projective coordinate, but some vectorial coordinate for z.
Sorry, can you ask the question again?
Upon this projective space is given by 4 number up to a scale.
Yes, that's right.
You need them actually not only up to the scale to get the lambda.
That's right. To get the lambdas, we need actually not a scale. However, so now let's finish the story, because remember, but we weren't interested in amplitudes all by themselves. They had to have some homogeneity under rescaling the lambdas. So you can ask the question again, what is the homogeneity on these guys? Okay? And on these guys, it is now incredibly simple, because now the mu's and the lambdas have the same scaling. They both scale like t. Okay? So exactly the same projectivization that took you to CP3 is actually the same one associated with this little group transformation that we're talking about before. You see, if I rescale mu and lambda by the same t, then that rescales lambda tilde oppositely than it does to lambda from this formula. Okay. So, and if I tell you now, this I won't explain, but there's also a formula, explicitly a formula for these eta tilde variables in terms of some new eta variables. which is exactly the same. So you see, when you have this picture, you've made momentum conservation completely manifest. The theory is supersymmetric, so there's some super partner to momentum conservation that we're also making completely manifest. And that's taken into account by also talking about some new Grassmann variables, a to a, not the original a to tilde a, but some new Grassmann variables, a to a. And the a to tilde a are determined in terms of the a to a by an extremely similar formula. I mean, it comes from a supersymmetric version of this picture. And so what we're finally left with after all this work, the same. So let me just say the sort of final story. So really, the data is now encoded by a variable that lives in CP3 with 4 extra fermionic coordinates. Okay, so the ZA are coordinates in CP3/4. Okay, so that just indicates that there's 3 bosonic and 4 fermionic coordinates. So these etas are some new Grassmann variables. Okay.
So you mean nothing could happen if you multiply both the z's and the eta by the same quantity?
Exactly. And in fact, the amplitudes precisely have that property, that m of TA, ZA are just equal to m of ZA. So they're honestly variables on CP3/4. Okay.
Before helicity minus 1 was eta tilde equals z.
That's right. Now,
What is the corresponding?
OK, so to actually pick out a particular helicity configuration from here is slightly involved. You have to go from here, you translate it back by here, and then you have to set the eta tilde here to 0. Okay, and so it's some particular combination of the components of these guys. It's not particularly I mean, there's nothing deep in it. You just have to there's some little Jacobian you have to compute, and it's right. But now the point is so now we're done with kinematics. Okay, I'm sorry it took an hour and a half to be done with kinematics, but these are the sort of best possible variables to use to talk about scattering amplitudes. Yes. Yes. Oh, I'm sorry about that. Oh, yeah, that may be important. Okay. Maybe I haven't used this board so much. So in summary now, we started off, just to summarize, we started off by having functions that depended on momenta and helicities for a non-supersymmetric theory. We went and we found that it was useful to introduce these lambda and lambda tilde variables. We still had the helicities floating around. We then added SUSY to remove these annoying lambdas and lambda tildes. Sorry, annoying these h's. So now we have nice smooth Grassmann variables. So that was sort of beating on the helicity part of the complication. We also then introduced these momentum twistor variables to completely trivialize all the constraints so that we finally have mn that just depend on these super z's, where I'll just write it again. The super z's are some mu's and some lambdas. Oh, some mu, lambda, and eta. So, but these are really some eta living in CP3/4. And all of the, so up here we had to say something about the homogeneity under rescaling. These things had to satisfy momentum conservation, All of that, it turns into here, is simply the statement that these coordinates live in CP3/4. That's it. Okay? Right. Sorry. Okay. Now, actually, it's more than that. The amplitudes they're really invariant under conformal transformations. They're invariant under SL4. They're not just coordinates on CP3/4, but they're invariant under SL4. Okay? If you do an SL4 transformation on the Z's, the answer is, if you do an SL4 transformation on the bosonic components of the Z's, then the answers are all invariant. Actually, they're super SL4 invariant. There's an SL4/4, and they're invariant under that. Okay? So now this is actually a remarkable fact. This is a very remarkable, very hidden fact in the Lagrangian. Okay? But I'll come back to it in a second. But the amplitudes are invariant under what you might call SL4/4. The generators of SL4/4 are, well, what you'd expect. So they're the four-dimensional generators of SL4 and some upper acting just on the Z's. Another four-dimensional transformation acting on the etas, which is just like in the SL4 symmetry that acts on the 4 eta coordinates. And then the fermionic symmetries that mix the two of them up with each other. So, yeah.
That means if you move all of the ZAs, all of the particles by the same.
Yes, it's all by the same one, all by the same group element. It's like a global conformal transformation, right? It's a global SL4 transformation, right? Really global SL4/4 transformation. The reason this is remarkable is, yeah.
What M is with value in them, because it cannot be purely even.
Sorry?
This M cannot be something purely even. Where does it take its value?
It is purely even. It is purely. I'll give you an example of what the, yeah.
Sorry.
The M's are the amplitude. The M's are the amplitude, and they're really. I mean, there's some rational. I mean, there's some functions of the Z's, and there are polynomials in the etas. Okay, so there's some polynomials in the etas, and they're rational functions they're functions of the Z's. Okay, at tree level, those functions are rational, but in general, they're something else. Okay. Oh, I'm sorry. Is that? Can I erase that now, Sasha?
Yeah.
Okay. Great. Sorry? Yeah, that's right. I'm sorry. I should have said it's GL here. Yeah, it is actually GL. Okay. If you like, the G part is just the special case of the rescaling of each coordinate individually. So yes, it doesn't make any difference. Okay. Yeah, let me just pause just to say some physics words about this, because this is a shocking symmetry that was experimentally observed by people who actually computed the amplitude. I mean, theoretically experimentally observed by people who were computing the amplitudes, and they discovered. I mean, they were motivated to draw this picture of the polygon from a number of reasons. Okay. But then they discovered experimentally that the amplitudes were invariant under inversions in this space. Okay? And that's truly a shocking fact. It's nowhere in the Lagrangian. What the Lagrangian for n equals 4 Super-Yang-Mills or any conformal field theory makes obvious is conformal transformations in the original spacetime. Okay? So in the original spacetime, the spacetime in which the Lagrangian is written, the d4x integral and everything, there is a conformal symmetry. And that's why there was the original Twistor space, and everything was about making that conformal symmetry as manifest as possible, et cetera, et cetera. So we expected a normal conformal symmetry. Okay? But this is a conformal symmetry in this dual space, in this space where this null polygon lives. And it was a very big surprise to find that second conformal symmetry. And you see, it's very dynamical. It depends critically on this planar limit, for example. Right? Only when you have the planar limit did this ordering make sense. And the ordering was critical to draw the polygon to begin with, to have this dual space make sense to begin with, and so on. Okay? But I want to emphasize that symmetry is completely invisible in the Lagrangian. And in fact, at tree level, it's equally well a symmetry of the pure Yang-Mills theory. It's much nicer to talk about in super Yang-Mills. But it has a descendant to the pure Yang-Mills theory. It could have, in principle, been discovered in 1955, when Yang-Mills theory was first written down. It's just a classical symmetry, but it wasn't discovered until 2007. So it's quite hidden, but it's a very powerful hint that there's something badly wrong with the Lagrangian, right? That if it obscures this incredible symmetry. And of course, this symmetry and the original conformal symmetry don't remotely commute with each other. I mean, they act on completely different spaces, and there is a big algebra which is obtained by taking the original and these conformal symmetries and commuting them all together. And this is this infinite dimensional Yangian symmetry that people talk about. Now, these Yangian symmetries have come up in the study of 1 plus 1 dimensional conformal field theories, or spin chains, but it's very bizarre to find them showing up in a very out-of-the-way place as having to do with the scattering of gluons in gauge theories. So, but these coordinates are actually so useful that it's kind of funny. We're going to spend all of our time in this dual space, making dual conformal symmetry manifest. Just because it's much more convenient to work in these variables than it is in the original Twistor variables, for a variety of reasons that I could tell you later. But I just want to emphasize this was a very big surprise. That there was a very, very big surprise that the amplitudes actually did enjoy these kinds of symmetries.
And when did you discover that?
It was found. In a really bizarre, out-of-the-way place by a group of people in France, Korchemsky, Sokachev, and their students and postdocs at the time, James Drummond and Johannes Henn. But there was really some sort of quite circumstantial evidence for it in a very weird, out-of-the-way place. But it was really Maldacena and Fernando Alday who vividly understood that it has something to do with this picture of the null polygonal this null polygon, and gave a sharp conjecture, actually, for a sharper conjecture for what this duality is. I mean, I could have mentioned something. I don't know if it'll be helpful. That you can ask. I mean, in the original space-time, what we're calculating has a name. It's called the scattering amplitudes. Gluons come in, they hit each other, they go out. There's this dual conformal symmetry. So surely there must be some natural question in the dual space-time that is equal to the original question that we asked, which was the scattering of gluons. And there is a natural question. What it is since you naturally have this null polygonal Wilson loop, I just gave it away. Since you have this null polygon, you can compute the expectation value of a Wilson line operator, Wilson loop operator, with the circumference given by that polygon. In other words, you calculate the expectation value in the gauge theory of the trace of the path-ordered exponential e to the I a dot a around this path. Okay, and that appropriately supersymmetrized, which wasn't done until just a little earlier this year, but anyway, that computes is equal to the scattering amplitudes in space-time.
You also need to specify how this gauge series is related to the one you started.
Right. But remember, all information about the gauge group disappeared in this large N limit. So it doesn't. You don't actually have to specify anything.
So it's the same series.
It's the same theory. Yeah. Okay. So this is already interesting. We started off with these quantities. We've discovered that they have another symmetry in another space, and in that space they have their own name. They're their own natural question, the expectation of this null polygonal Wilson loop. But neither on this side nor on this side is the full symmetries are the full symmetries of the theory manifest. Okay. It's quite reasonable to expect that there must be some formulation where all the symmetries are manifest, but in that formulation, neither space-time is going to play a particularly important role. It's going to be a quite space-time removed set of ideas. Okay? And that's what I described in my talk last week. Okay? So there's a third structure here, which is this Grassmannian. Okay? So there's a simple contour integral over a Grassmannian that seems to be that seems to be the most invariant way of talking about the theory. And you can interpret it. You can give it two different space-time interpretations. One as a scattering amplitude, the other one as a Wilson loop. But it's something more fundamentally sitting there, which makes all the symmetries of the theory manifest. And now, but I mean, I've gone for an enormously long time. So.
Yeah. No, I actually have to be in New York the next 2 days, but the next day I'm here, so on Friday, I think the room is free on Friday.
I mean, I don't want to try your patience too much, but
I'll be here.
okay.